let's discuss non-conservative force. So non-conservative forces are forces in which their work done is dependent of the path. So the work done by non-conservative force depends not only on the initial and final position, it also depends on the path you take to go from the initial position to the final position. So the commonly seen non-conservative forces are the kinetic friction and external force. But in this situation over here, we will try to prove that kinetic friction is a non-conservative force. How are we going to prove it? We are going to set up an initial position and a final position, and we will create two different paths to go from the initial position to the final position. Once we have set a two different paths, we will find the work done by kinetic friction to go from the initial position to the final position using path 1. And we will also find the work done by kinetic friction when the object moves from the initial position to the final position using path 2. So if path 1 and path 2 give you the same amount of work done, then it means the work done is independent of path, then this kinetic friction will be a conservative force. But if path 1 and path 2 give you different answers for their work done, then that means this work done here is dependent of the path. Then kinetic friction will then be a non-conservative force. So it depends on what answer do we get for path 1 and path 2. So let's get into it. So let's say we have a table here, and this table is a rough surface with a coefficient of kinetic friction of 0.2. Now you set up the initial position and the final position, and both of these positions here are on the table. So you have a table, initial position here, final position here, all happening on a flat surface. So you create two paths to go from the initial position to the final position. The first path is a direct diagonal path connecting the initial position and the final position. So we can say this journey here takes 10 meters and it's 30 degrees above the positive x-axis. The most direct path from the initial position to the final position. We call this path 1. Then for path 2, we will follow a zigzaggy pattern similar to the example that we have discussed in the gravitational case. So we have an object moving zigzaggy until reach the final position. So everything here is happening on the flat table, so you can think of it as the object move 5 meters to the right, 2 meters forward, 3.66 meters to the right, then another 3 meters forward until we reach the final position. So this will be path 2. And we'll be interested to find the work done by kinetic friction when the object moves using path 1, and we'll find the work done by kinetic friction when the object moves using path 2, and we will check whether they are the same or not. So for path 1, we have to determine the direction for the displacement, and we determine the direction of force, and from there we determine the angle between the force and the displacement. So this is the equation that we will follow. The magnitude of kinetic friction and the displacement, both of them are magnitude, then cosine theta, where theta is the angle between the vector for kinetic friction and the vector for displacement. So for this path 1 over here, we know that the displacement will be a vector connecting the initial position to the final position. Whereas the direction of kinetic friction, since we know that kinetic friction is always opposing the direction of sliding. So since we know the object is sliding in this direction on the table, we know that the direction of kinetic friction will be opposite this direction of sliding. So therefore, you should see these two are pointing in opposite direction, and therefore we know the angle between the kinetic friction and the displacement are 180 degrees. So once we know the angle is 180 degrees, like usual case, I only care about angle. So what I do is I substitute in the angle 180 degrees. Then cos 180 degrees according to trigonometry is -1. So we know that our work done by kinetic friction, if we use path 1, be just negative kinetic friction times displacement 1. Of course, you can find the magnitude of kinetic friction by taking mu k multiplied by normal. In this case, the normal is just equals to the weight. So you can get your magnitude of kinetic friction, you can get your displacement, which is 10 meters. So you do the calculation yourself and you arrive at an answer, which I will not put here. Okay, because I'm focusing on whether they are the same or not. And I think I can prove it without showing you the exact number for the work done. Okay, so this is path 1. Let's move on to path 2. So path 2 is a zigzaggy pattern, similar to the example for the gravitational case. We will break this work done into 4 different parts, which represents the 4 different sections of the journey taken. So we will have a section we have displacement 2a, which is for path 2, section A. Displacement 2b will be for path 2, section B. Displacement 2c will be for path 2, section C. Displacement 2d will be for path 2, section D. So we will find the work done for each section of the journey, then we will sum them up to find the kinetic friction, to find the work done by kinetic friction for path 2. So again, I'm more interested with the angle, which is theta 2a, theta 2b, theta 2c, and theta 2d. And I believe based on your understanding that kinetic friction is opposite the direction of motion, you know that all these angles here should be 180 degrees. But let's show it explicitly in the diagram. You can see that if for the first portion of the journey, you are moving to the right, therefore the direction of friction is pointing to the left, and angle between them is 180 degrees. Same for the second section, you're moving forward, so your kinetic friction is pointing backward, angle between them 180 degrees. Third section, moving to the right, kinetic friction to the left, angle between them 180 degrees. Last section, object moving forward, and the kinetic friction pointing backward, angle between them 180 degrees. So all of them will have an angle of 180 degrees, and according to trigonometry, cosine 180 is just -1. So you can know that all of these values will be -1. So you see that all terms here share a same -1 and the same kinetic friction. So you can factorize out the negative and you can factorize out the kinetic friction. So what you get is negative kinetic friction, bracket, then inside the bracket you have the summation of all the sections that we have traveled through just now. So indeed, actually what's inside the bracket here is just the total distance traveled by the object using path 2. Okay, so now I'm going to do a direct comparison between path 1 and path 2. You can see that both path 1 and path 2 shares negative kinetic friction in front. But for path 1, the displacement is just S1. For path 2, the part behind is the summation of all sections of the journey. We know that path 1 is the shortest distance between the initial and final position, whereas path 2 will be a quite long distance because it's not the most direct path from initial to final. Therefore, we should expect this value, S2A plus S2B plus S2C plus S2D, to be larger than S1 over here. And if this summation is larger than S1, then we know that the work done by kinetic friction in path 2 will be larger than the work done by kinetic friction in path 1. So path 1 and path 2 will result in different work done by kinetic friction. Therefore, we can say that work done by kinetic friction is not the same for different paths. And if different paths produce different amount of work done, that means the work done itself is dependent of the path. Different paths will result in different work done. Therefore, kinetic friction here, we have successfully proved that kinetic friction is a non-conservative force. Okay, so this is a rough example of conservative force. You can do the same for external force as well. But in the next video, what we will do is we'll relate the idea of conservative force to the idea of potential energy by relating potential energy with the work done by conservative force.